Hello, everybody, and welcome to 2021. We are pleased to have for our first IE2 seminar, Marcus Lapeyrolerie and Carl Boettiger from Berkeley. Marcus is a second-year grad student in Carl's group. He came from doing physics at Caltech, and Marcus has been at Berkeley for some amount of time now before he did his PhD at Davis in pop bio and did a postdoc in applied math and statistics at Santa Cruz. I know Carl has been working for a long time on doing really great work around open science and reproducibility, did some phylogenetics, and but these days mostly ecosystem management and ecological forecasting. Marcus, I know less about because he's just starting, but it looks great. So I think Carl's going to start off and hand it off to Marcus. Go ahead.
Sounds good. Thank you, Peter, for the invitation. It's great to be able to join you all here and have this opportunity. And it's also great to be able to share with Marcus this chance. I'm going to be talking a bit about kind of the conservation past, setting up some historic context, and then quite appropriately kind of hand it over to Marcus to talk about what might be a vision for sort of conservation future and some of the newer methods that we have been looking at. And then looking forward to folks sticking around after to talk. We can also, I think there are connections from this work in dealing with model uncertainty back to work that I first met Peter doing in phylogenetics, looking at model uncertainty as well, albeit in a different context. So you may see echoes of some of those themes here as well. So conservation decision-making under uncertainty, from MSY to ML. We'll get into acronyms as we go along. So first, what is conservation decision-making and why am I talking about it? It almost needs no introduction. We face so many great challenges in the world today, from our changing climate, warming, to the consequences thereof, increased fire danger, as this past season in both California and Oregon was such a testament to managing global fisheries and other natural resources, to more terrestrial examples, transitions from agricultural practices at sort of factory scale to more diversified and perhaps more ecologically valuable farming systems. To the outbreaks of pests such as the pine bark beetle, which is again a major problem here in the West. And again, a slide that needs no introduction in the role of viruses driving global pandemics. So we'll have a chance to look at some of these examples. They all share some common challenges as far as what to do. You know, we face these great problems. We know that there are these problems, and what are we going to do about it? So here's my kind of pensive polar bear, just kind of staring off into the melting ice and thinking of solutions. One thing that I think these problems have in common is that most of them are what we would classify as sequential decision problems. So what do I mean by that? Well, you can think that there is some sort of state of the world, right? And you have to decide what to do. You have to decide an action. But this problem doesn't just kind of go away when you do the action. You don't get just one action. You know, the system responds to that and you observe it in a new state and you have to do a new action. And then again in a new state and a new action. So really it is like a game of chess. And that sequential feature means that it has that core aspect of chess where you must plan multiple moves ahead to be really effective. You know, that you can't always go for maximizing taking the most valuable piece now. That might put you in a bad situation several moves down the road. And such problems pose a challenge for coming up with good strategy and mean that we can't just do kind of short-term thinking. So I'll be talking about some examples of how that arises in conservation and what we do about it. So in this, I want to sort of zoom back more broadly into what is sort of the role of theory and modeling in guiding conservation. It is often assumed that these problems are really problems of policy, you know, that we more or less know what needs to be done in conservation. And the problem is merely a lack of political will, perhaps, to do it, or financial will, but it isn't really a science question. And while I think that is an important component of the discussion, that doesn't remove the very specific needs of knowing exactly, it's one thing to know that we must address this problem. It's another thing to know of the available actions to us, which ones do we take and exactly how do we go about it. And theory has a lot to play in both sides of this equation. So I'm going to invoke sort of Lord Robert May's distinction here between the different roles that we use, theory and models today. There is kind of a sense in which a model is strategic in making a decision, meaning that it isn't specific to one particular problem. Parameters aren't all estimated to be specific to that exact pandemic or that specific city or the details on the ground, but to guide thinking overall. A model may be used in a very different way that Lord May describes as tactical. So this is where sort of the opposite is true. The model is specific to a particular context and is unlikely to generalize, but has really concrete proposals about what to do. We are going to see both sides in play in decision making. I think it's easy to kind of assume or forget this distinction. And so you might think that some of these models, because they are talking about specific decisions, they sound tactical, but we're actually using them in a strategic context in the sense that they're not fitted to any particular species or particular detail. And the reverse will also be true, where these are really only useful in a tactical context and they're not giving us a strategic insight. Another thing that I will highlight is, what are we trying to do anyway? What do we mean by solve a conservation problem? What do we mean by the optimal solution? It is often natural to think of this in what I will call engineering terms. The optimal means that we have some omniscient manager in charge, who has some objective, and they are trying to maximize that objective, perhaps, to reduce climate change as fast as possible, to save as many of the species as possible. It's important to realize that in this field of decision making, we see optimal used in a much more emergent sense. And this can borrow from other areas of ecology, such as behavioral ecology, where optimal is assumed to be the outcome of some ground up process, in that case, evolution. And the behavior of an organism is just assumed to be optimal. And if you don't see a match to that behavior, it is because we, in our models, have made some mistake and we're optimizing the wrong thing. The same approach is used in policy, particularly by economists, who assume that given the right settings, the market forces will lead to some optimal behavior. And that if the behavior that we want is different than that, it is that we have to alter the reward functions underlying and not change, dictate the behavior from above. So these are kind of two different ways to see. We'll see these play out as we go in here. The last theme I wanted to stress is the theme of uncertainty, which has been central to my research pretty much from the beginning. You can think of uncertainties in different classes, and I'm going to use these three. So there's uncertainties that are intrinsic to the process: stochasticity, environmental noise, demographic noise, things that are a result of the process being fundamentally not deterministic, or rather not deterministic at the level of the state variables that we think of. So kind of, you can't get rid of that. Next is observation uncertainty. This is not part of the process. It's only due to the fact that we have imperfect instruments. And therefore, it presents the option that perhaps with better instruments, you could reduce observation noise. But it plays an important role, as we shall see, in how we make decisions, particularly when we talk about conservation, where these things are really hard to measure. And the third fundamentally different kind of uncertainty I see is called model uncertainty, or I'm referred to as model uncertainty. Now, this represents what we don't know about the process. So unlike process uncertainty, this is reducible. We could learn more about the process. This reflects only the ignorance of our manager. It doesn't reflect something fundamental about the world or about our tools to measure. And we will sort of tackle each of these in turn. To make this a little more concrete, I'm going to focus on a classic example of optimal harvest, or the concept from the title of maximum sustainable yield. And we'll see how these have played out before I hand over to Marcus to kind of lead us forward into a more ambitious way to address some of these challenges. So in my standard professorial style here, I'm going to take you way back to 1954, before we had computers to do our optimization for us, for the most part, to the classic work of Schaefer at the same time as the work of Gordon in defining what we now refer to as maximal sustainable yield. So you will all recognize the logistic curve here. So here I have the growth rate, how quickly this population is growing as a function of the population size. And you will quickly identify for me that there is a stable point at the carrying capacity here at 100, where this growth curve crosses the line of 0. There's an unstable point at 0, of course. And you can quickly solve this to say that the maximum sustainable yield occurs at a biomass of 50 here because that's when the growth rate is maximized. Blah, blah, blah. What does that all mean? So the population will be sitting here. If it's unfished, you'll want to fish it down to this size so that the population is growing at its fastest rate. This will allow you to harvest consistently at the excess growth, right? So this population will then grow a lot, boom, by, you can easily solve for this, a factor of RK/4 in the logistic model. And then you can each year harvest this for free and the population will return back to this maximum growth size. There are various ways to do the proof, but the graph is pretty convincing. Just for context, in fisheries, and particularly marine fisheries, we often think of this not in terms of harvest, but sometimes in terms of mortality. So this means that if you apply this fishing pressure, think number of boats or number of hours fishing, to a biomass at this size, you'll get this harvest. Now, this is important because if you apply this maximum sustainable effort when the biomass is smaller, this doesn't mean the population crashes. As you can see, this is less than the growth rate, so the population will grow, albeit slowly, until it gets here. And then if the population is bigger than this size, the population will shrink, albeit slowly, until it gets to here. So in the long term, doing this effort will always get you to this biomass. Of course, if you stuck with this harvest, this would be too high if the population was, over here and therefore had a too small growth rate, and you would crash it. So little subtlety to keep in mind. So this was the state of the world. There is no uncertainty in this model, as you saw. I know the process exactly. The process has no error. I know the population size, and I have only this asymptotic no dynamics result. So it took from 54 up into about 1973 for Jim Clark to give us the constant escapement solution, which is how we do salmon management and some other fisheries where we know the population sizes quite well. And it says, well, if that's the size you want to get to, you should want to get to there as fast as possible. Meaning that if the population size is below that size, you don't just sit there fishing at your MSY effort. You just close the fishery entirely so that it can recover as fast as biologically possible to the optimal size. And that is not only the best thing in terms of the fisheries, the species recovery, but also in terms of economics, that you will make more money because you won't delay your getting to this maximum yield. Likewise, if the population is bigger than this size, you don't fish it down slowly. You get it back to this optimal size as fast as possible. This is what's known in the jargon as a bang-bang solution. You're always trying to get here as fast as possible. You can't put fish into the sea most of the time, though often you can, but that would be, you're basically trying to get here. So this is the constant escapement solution, meaning that it's always here below this maximum, you don't fish at all. So zero, there, the fish are still, you see this is the one-to-one line, but up to here at this BMSY, you're always fishing back down, so you're always leaving the same number of fish in the sea. That's what we call constant escapement. It's going to be relevant in a minute, because folks have looked at this since about 1973 and said, what about uncertainty? Again, we've assumed we know everything. And there's a lot that depends on us knowing everything, because you've just said we go bang full speed to that result. What happens if the population is stochastic? Intuition would suggest that we should be cautious when we know less. If we know less about the system, maybe we shouldn't fish it quite as much. However, it didn't take long before in 1979, Reed was able to complete the proof, which I'm showing the statement of here, which says basically, if you add stochasticity, so this is process uncertainty, the fundamental underlying uncertainty, you get the same result. You don't be any less certain. You just do the exact same policy as if it was deterministic. Uncertainty doesn't matter. That kind of surprised me as someone who had thought a lot about uncertainty in different ways. And where do we go from there? Well, process uncertainty. Folks had kept on scratching their head on this paradox until we get to Clark revisiting this with his student Kirkwood in 1986. And he says, I think I know why there isn't, why you don't become more cautious. Basically, Reed's problem was too simple. You see, in Reed's problem, observation error wasn't there. And because observation error isn't there, you get to measure the system each time. Remember, it's a sequential decision game like chess. And you can, like chess in Reed's view, you could see the whole board. You knew exactly where the pieces were. And so the fact that there was imperfect measurement or imperfect stochastic growth didn't really matter, because that stochasticity, you got to observe the result before you set the harvest, it was all gone. So he went and added observation error in, and whoops, with two kinds of error, instead of becoming less cautious, you got more aggressive in fishing. For a lot of the time, you can see here, this line in particular, you are overfishing the population, leaving fewer fish in the sea than in the optimal escapement solution. So that was funny. They scratch their head in the paper, of course, and they say, this result appears to contradict the conventional wisdom of renewable resource, where you should be more cautious. But as all good academics can do, after noting that this is weird, they kind of wave their hands enough to say, no, it really does make sense. Just believe us. Well, not everyone was convinced. Costello and colleagues looked at this a little bit later in 2005. And again, they said, well, if you look at it, Clark and Kirkwood kind of took some shortcuts to do the math with the uncertainty. We're going to try to take fewer shortcuts. And so here they, after a long story short, look at the same problem with careful implementation. Here's with measurement uncertainty. And they find an even more dramatic version of that result, that you are letting fewer fish escape when you were uncertain about the stock size than when you were certain. Uncertainty is making you even more aggressive. And they too kind of scratch their heads and say, it may seem counterintuitive, blah, 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 that we would see this behavior. But they also mentioned that they had to make some assumptions to get to it. And after a bunch of hand waving, they say, you should believe us. But these assumptions, which, we get so used to reading papers with assumptions, we don't pay too much attention to them. So it took me several years of rereading this paper before the assumptions caught my eye. I've highlighted one here, that one of their assumptions was that they use only the current measurement when forming expectations about what the optimal solution should be for the next harvest. And they point out at the time that, this is no longer really perfect because there is measurement uncertainty. The system isn't fully Markovian in the observed variable. Past measurements now have some information. 10 measurements is better than 1 measurement if you have measurement uncertainty and you're trying to get the true value. Now, if you have perfect measurement accuracy, then you don't care about the past, right? That's what it means to be Markovian. And so they basically just kind of assume that away, and they say, that would be too hard. It would be very complicated. Let's not do it. We will see that that assumption has consequences. Luckily, in another world, back in 1971, this same problem of partial observation was being studied by a rather different group of people who took their first examples from many of the same works that we were looking at very beginning by Schaefer and Gordon on resource management. But quickly they were moving over into a completely different field, which would soon become known as the field of robotics. And so here we have a description of the first algorithm that could actually solve, without making that shortcut assumption, this partially absolved Markov decision process where you don't have perfect information. So again, to kind of jump to the case, it took until about 2008 before computer science went from a field of here is in theory an algorithm to here is the implementation of a very efficient particle filter based approximate version of that optimal algorithm that you can run on realistically large state spaces. And so we were just able to borrow this from robotics in work in 2008, wrap it up in a little R package so that we could call this implementations from R and run this on our fisheries problem and show the following, that you do indeed find that your intuition that you should be more cautious is almost always true. What does that mean? Well, you actually can't think of this purely in terms of a policy function, meaning in terms of for any observed stock size, what is the policy that you should do? For precisely the reason that they just told us about in Sethi's comments, that all the previous observations matter. But you can summarize those previous observations in terms of a belief probability in terms of the true stock. So if looking at all of the previous measurements, you believe the true stock was rather small, but you get an observation that's quite a lot bigger, well, then it shouldn't surprise you that indeed you're very conservative. You say that observation was probably crap, and really I should be very careful and let many more fish escape. Meanwhile, if you're quite confident that the true population was very large, then there is at least some of the time where if you see a value that looks like the true population is small, that's probably due to measurement error. And maybe it's okay to set a policy that looks like it's overfishing because after all, the population is probably larger than you thought, and so you're safer to fish. But on average, you're going to, you said there isn't a single constant escapement solution. You can see this curve is not constant escapement at all. I overlooked a bunch of papers in economics that restricted themselves only to finding papers that had economic constant escapement as the answer. It's a little more nuanced, but in general, you find that you are more cautious. And this actually matters. We're able to revisit papers that had previously assumed this constant escapement was the optimal thing to do. In a traditional economist twist, they called this rights-based fisheries management. They said, if you created a market-based system, which we don't have for fisheries because it's managed only year to year, where you can benefit from future years. If you created that, they said, then economics would do its magic hand and fisheries would do the optimum. And they said, what is the optimum? We need something to stick into our simulations. It must be constant escapement, the MDP, the Markov decision process solution. And if you put that in this fisheries cover very quickly, well, we turned that on its head and said, if you ran with that MDP problem, but in fact, you did not have perfect observations like they assume, you would find that depending on how bad the measurement error was, well, if there was no measurement error, you would do just like they said. But as this measurement error got worse and worse, with 20% measurement error, you would actually overfish dramatically with MDP. In fact, even worse than business as usual. With 10% error, you would still be doing pretty badly. But you could account for the observation error here using the POMDP techniques that I alluded to from the robotics work. And by accounting for that, we were able to, despite the measurement error, still get strong stock recovery in all of the global stocks considered in this example in Costello's original paper. Okay, so that's more or less where I wanted to get up to. We've been able to kind of slowly incorporate some of these uncertainties and see that they make a difference to outcomes. But there's still a lot of strong assumptions in that work. We have still said that we know the underlying model. We have only said that we know the model has uncertainty in both the observations and the process. And as, of course, our reviewers enjoyed pointing out to us, this is, again, almost never the case in ecological systems. But the trouble is these classical techniques, and even the very more modern methods like POMDP, they scale very badly to adding a lot of model uncertainty. And so you're relatively constrained with the kinds of systems that you can consider, both in terms of the size of the model and the number of possible models. So in a search for breaking out of that, we are now looking at approaches in deep reinforcement learning. And I'm going to try to turn over to Marcus, I think, here to talk a little bit more about what is deep reinforcement learning, particularly model-free deep reinforcement learning, and what we've been able to do with it so far. So thanks. I'm going to stop share here, and Marcus, pick up.
Hopefully everyone can see. All right, cool. So now we'll transition into the research that we've been focusing on over the past 9 months or so, which is applying model-free deep reinforcement learning to decision-making problems in conservation. And before I kind of jump into our research that we've been doing, I want to give a little bit of background on what reinforcement learning is, as I imagine it's a new topic for a lot of people here. And in this, I'll say that the overall objective of reinforcement learning is to design an agent to interact with its environment such that the agent will learn how to maximize its cumulative rewards. And the basic paradigm of this reinforcement learning problem, I think, is most succinctly shown in this schematic here, where the agent is able to perform actions, and as feedback, the environment will determine what the state will be at the next time step, and the environment will also determine what the reward will be for that action. In common across all of reinforcement learning, the basic process is that initially you will have what's called a training period, which is where you kind of let your agent explore the environment. In other words, explore the state action space. And the hope is that eventually during this exploration, the agent will have some trajectories in state action space that have a high cumulative reward. And the task for the agent is to update its behavior so that during test time, it will be more likely to revisit these high reward regions of state action space. And so far, I haven't really mentioned how neural networks are involved here. And in this, I just want to say that there are a lot of different approaches that one can take in approaching this reinforcement learning problem. And in this, there are also a lot of different ways that one can incorporate neural networks into this problem. But for this talk, I'll just outline kind of what I would consider to be the most straightforward model-free deep reinforcement learning class of algorithms, which are policy gradients. So in place of the agent here, we have what's called a policy neural network. And all the policy network is doing is mapping states to actions. So as input, it will receive the state at that time step, and then it will perform some series of operations on it. And as output, it will output what is the action for that state. And kind of the idea here is that during the training period, once again, you kind of hope that the agent will come across high reward regions in state action space. And it will, once it observes these trajectories, it will basically update the parameters in this network so that it will reinforce the behavior that led to that high reward region in state action space. And we've been greatly inspired to kind of take this line of research because deep reinforcement learning has made a number of remarkable achievements in the past kind of 6 years. And the first landmark paper was published in 2015, where a group was able to train an agent using reinforcement learning to achieve superhuman levels of performance on some of the games in the Atari video game suite. Then in the next year, another group was able to train an agent using reinforcement learning to defeat the master champion of Go at the time, Lee Sedol, 4 games to 1. And if you don't know, Go is widely acknowledged as the most complex board game in the world, even more so than chess. And this was considered potentially as a feat that AI would not be able to overcome. And then in this past year, an agent also trained with reinforcement learning was able to predict the 3-dimensional structures of proteins at the levels of resolution that can be determined experimentally. And when I began my undergrad, this kind of protein prediction challenge was considered potentially as an unsolvable problem. So it's amazing that it apparently has been solved. But I will definitely add some grains of salt here, which is that it can be very difficult to get deep reinforcement learning to work in practice, even for environments that you would imagine would be easy for an agent to solve. And there are many reasons why this can happen, but I'll just try to outline some of the most prominent ones that are frequently come across. The big, at least one of the big kind of theoretical challenges in reinforcement learning algorithms is how to deal with sparse reward structures. So imagine that the agent is tasked to learn in some environment where a non-trivial reward is only kind of given at the last time step. And there's like a long sequence of actions kind of before that. It's very difficult for the agent to kind of assign credit here, basically to decide, what's the sequence of actions or what's the subsequence of actions that resulted in this reward. In practice, deep reinforcement learning algorithms also have a lot of, particularly model-free deep reinforcement algorithms tend to have problems with instability in terms of their hyperparameters. So for instance, when you, in the policy gradient example, you randomly initialize your policy network. Let's say you randomly initialize with 1 seed and you do training, and let's say your agent does spectacularly well. And then on the next training round, you initialize with another seed. It wouldn't be uncommon for the agent to then perform spectacularly poorly. And yeah, this really is a big problem in practice. Also, a lot of the model-free, a problem that plagues model-free deep reinforcement algorithms is sample inefficiency. So it tends to take a lot of interaction with the environment for an agent to develop any decent policy. And lastly, RL algorithms tend to only work for very specific tasks. So imagine if I want to kind of learn over like a range of models or kind of a wide range of model parameters, deep RL algorithms tend to really struggle with this. And to date, there really hasn't been kind of a wide application of deep reinforcement learning in like the conservation space. So our basic kind of research question is, can we use these methods as effective tools for decision making here? And one big inspiration for us has been in a software package called OpenAI Gym. And the basic premise behind this package is that it allows users to create standardized reinforcement learning environments. And it also allows users to benchmark their solutions on these standardized environments. And so here I have just a screenshot from one of the OpenAI Gym leaderboards. And so they describe like one of the reinforcement learning environments that they have. And for this environment, users can submit their solutions. And these solutions are ranked according to some performance metric. And with each submission, there's also a write-up to describe how these solutions were developed. And so like kind of the main premise here is that OpenAI is trying to foster an open science approach to solving reinforcement learning problems, which is great in terms of reproducibility, which I mentioned before can be a problem with reinforcement learning, but also kind of, I think it's going to be the best way to make rapid progress on these difficult problems by kind of taking this collective approach rather than having people work in their own silos. So a primary focus of our research is really to replicate the OpenAI Gym and to make a suite of conservation kind of oriented OpenAI gyms so that we in like the larger community can benchmark performance on deep RL algorithms on these specific problems. And in kind of trying to achieve this purpose, the first gym that we've developed is a fisheries gym. And here, like the basic process is that you have an agent. The agent is able to set a quota, which functions as its action. And then in turn, we have various models that we can plug in here for the environment. But the process is the same where the environment sets the catch for this quota, and the catch functions as the reward. So here the objective is the same as Carl talked about it initially, which is to maximize kind of the cumulative catch. And the environment also will set the population for the next time step. And so at the moment, we've implemented a range of growth models, including logistic, Allen, Beaverton, Holt, Myers, May, Ricker, non-stationary, and tipping point. And these are all things that can easily be kind of swapped out. Or basically, you can just plug and play all these models for the simulated fishery box here. And we also have plans to add model complexity here because at least at the moment, everything is just a single species kind of homogeneous scenario. And there's also just a single agent, which is not realistic. So there's definitely a lot of work here to make everything more realistic. So we're kind of just at a preliminary phase. But in this, I'll say that we've been a bit limited in that the biggest kind of time bottleneck that we've experienced is just in benchmarking all these different RL algorithms, because it's, as I said before, there's like a lot of different ways that RL can go wrong. And it's also a fairly computationally intensive process to tune and to train these algorithms. And here, I just wanted to show kind of like a preliminary version of what we have in mind for a leaderboard. So in this first entry here, we list an agent that follows a constant escapement policy. And this is, sorry, I should mention that this is for a logistic growth model that has a stochastic term. So this agent here in this first entry follows a constant escapement policy, and here we list the cumulative mean catch, and we list this in absolute terms. And in this next entry, we have like an agent that's using an MSY policy, and everything else here are all RL trained agents. And the mean cumulative catch is listed for these remaining entries as a fraction of this constant escapement entry. And we can see that a lot of the RL agents seem to be performing fairly well. And in particular, this A2C trained agent is coming very close to replicating the cumulative catch that's seen with the constant escapement policy. And to the right here, I just show some state action and reward trajectories from this A2C trained agent. And kind of as expected, it's like replicating this constant escapement policy fairly well. And kind of one of the most powerful things about using these model-free algorithms, and I failed to mention this before, so I just want to bring this up, is that for these RL agents, we aren't really using any assumptions about the environment. They're learning kind of on their own. We're just, initializing with some neural network, and that's it. So that's, I think, one of the most powerful kind of parts of using deep RL to solve these problems, especially in cases when, if we build up kind of complexity in the models so that, our assumptions become less and less true. I think that using RL agents could potentially be a very powerful tool. And I just want to encourage everyone to play with our Fisheries Gym on your own. It can be installed through Pipey, which is a Python website that helps with distributing software packages. So you can just from the terminal just do pip install gym fishing, and the GitHub repo should be accessible through our lab website. Yeah, we definitely encourage everyone to see how it's implemented and try it out if you're interested. Also, we've been working on an epidemic gym. So early on in the COVID-19 pandemic, we came across this great paper that talks about optimal control methods for the SIR model. And if you don't know, the SIR model is kind of like the standard toy epidemic model. And kind of at the time that this paper was coming out, we were seeing like a range of different non-pharmaceutical interventions. And this paper kind of examines, if an agent is to intervene with this SIR model under like certain types of interventions, like what's the optimal way for this intervention to happen. So in OpenAI Gym, we've implemented the same epidemic model. So it's the same basic SIR model that allows for some of the methods of intervention that are listed in the paper. So the basic kind of process here is the agent kind of decides the timing and intensity of a non-pharmaceutical intervention. And in return, the model describes what the population will be at the next time step for the relevant populations. And it also, as the reward, feeds back to the agent the negative of the peak in the infectious population. So the objective here, as it was in the paper, is to minimize the peak in the infected population. And here is another preliminary result that we have that shows how an RL trained agent is able to perform in comparison to what the optimal solution is. So the optimal here is shown in blue, the RL train agent in red. And here I'm just showing how well the agent is able to time interventions, and this is over a range of model parameters. And we can see that the agent is able to kind of get the general like kind of functional form of the intervention in terms of timing, but there is a little bit of a bias. But I will say like we could do more tuning here to maybe close the gap. But I still think at the moment this is pretty decent result to have obtained. And I'll just mention here that I trained this reinforcement learning agent here over a range of initial states, in addition to training it over a range of model parameters. And this was kind of the main difficulty here. Like I was able to train an agent on like a very narrow, let's say like range of model parameters, or just on like one initial state, and it would be able to replicate the optimal solution exactly. But as soon as you tried to like generalize across a wider range of model parameters and like a wider range of initial states, then you would start to see this kind of gap between the RL agent and the optimal solution. And this is again available through Pipey, so we definitely encourage people, if you're interested, to check out this gym. So it's simple pip install gym_epidemic. And likewise, the GitHub repo is publicly accessible, so you can check out how it's implemented. And yeah. Additionally, we have some more kind of OpenAI gyms that we're developing. We have a range of gyms that focus on kind of more specific kind of species conservation tasks. I've also been working on a wildfire gym that implements a cellular automata model, and the objective there is kind of to suppress the wildfire. And recently, we've also been working on a climate change gym, which implements Nordhaus's DICE model. So it kind of looks at, what's the best way to allocate resources to reduce emissions in society. So in parallel to kind of all the application of RL side of things, we've also been looking at, kind of the ethical consequences of using these new and potentially very powerful tools. And my fellow lab mate, Millie Chapman, is kind of leading the charge in this. And this is also kind of in a preliminary stage, but we think it's, very important to think about these kind of ethical problems as well. So with that, I don't know if Carl wants to add anything else, but I'll.
Yeah, that's great. Let's open up to questions. Thanks, Marcus.
Couldn't hear you, Carl, but let's thank Carl and Marcus somehow. Yay, everybody's clapping right now. Now, what did you say, Carl?
Oh, I just said thanks, Marcus.
Oh, yes, thank you, Marcus. So, so you want to take questions now?
Yeah, and should I?
That would be great. And
should I stop the share or just leave it up?
Well, let's see. Somebody might want to ask questions about the slides, but Monica has a question in chat. I'll read it. Thanks for the interesting topic. Years ago, I worked on a USAID program for small-scale fisheries monitoring in Indonesia. And the main problem in my country, besides illegal fishing, is spotty fisheries data. Boats under 25 units of mass, the GT, don't need to report their catch, while the majority of them are using small boats. How to incorporate these kinds of uncertainties, limited data, illegal fishing in the model, and eventually in policy? What do you think is the best tactical strategy in this kind of situation?
Great question, and an important one to address. I think there's different ways to go about it, but the first step is recognizing that uncertainty is just a major problem in implementation, right? And so we still have many policies that are based on perfect knowledge, or at least don't acknowledge that they are, but they take an MSY policy and they say, oh, we should do total allowable catch. It should be, back off from the maximum by 20%, but they don't build in from the ground up the fact that the measurement is uncertain. So by introducing measurement uncertainty, now we have just introduced it in a generic way, saying that, oh, measurements are distributed log normally or Gaussian or whatever with some parametric thing, right? But that's a first step into understanding what is the consequence of the real measurements being different than what the reality being different than what we have measured. So that's kind of only the tip of the iceberg there to say that, oh, underreporting is measurement. Of course, in reality, those aren't just asymmetric uncertainties, but those can introduce very biased uncertainties. You can put that into your distribution for your measurement uncertainty and still run POMDP. That still isn't using all of the information, perhaps, of how you know the cost of certain biases, but it's kind of moving you closer to that direction, and you can kind of see what's the result of like the policy that you need to recommend as a result. One thing that's nice about the work that Marcus highlighted is that it gets much easier to add this complexity without the whole thing breaking. So the RL algorithm, as you mentioned, like you don't need to start by saying, here is my model, here are all of the assumptions. You just start with some process. We're using simulations of the process, but if you want to add complexity, it's much easier to add it to the simulation. And the neural network doesn't care. It just says, I'll have to watch it longer. If you want to add it to the classical methods that you would solve with pencil and paper or MDP, you quickly go from this is easy to I can't do this. So I think it's a step in that direction.
Did you have anything to add, Marcus?
No.
Okay. All right. Any other questions? You can either just say so or raise your hand if you want to get in line.
Just while we're waiting for questions to kind of pop into the chat, I thought I would also kind of, in the spirit of the previous question, I think this also addresses some of the ethical questions that Marcus was alluding to right there. So we just kind of tipped our hat to, there's kind of two things that can shift here. One is just changing the way that we make decisions, but there's also perhaps an undesirable consequence of changing how decisions are made. If we are moving from a decision support tool where the actual details are still sort of haggled out by human beings to an algorithm that says, this is how I think things should be done. We also should think sort of who owns that algorithm or who owns that data. Is that algorithm sort of part of a public process and a public result? Or is that just being, you mentioned the legal fisheries, is that just Google Fish Watch telling us, according to their proprietary algorithms, where illegal fishing is and is not occurring? And as you pointed out, the data can be biased. How do we know that that data is not biased? So I think there's a host of decision-making questions that come out that are both ethical issues and also issues of politics or power. We've been collaborating with a sociologist who specializes in the science policy to try to get a better handle on that, as well as a bioethicist. And I think sometimes when we have spoken about these problems, some folks recognize immediately, oh yes, we think there are also ethical concerns. And sometimes we get pushback that, oh, well, if the artificial intelligence is not being trained on human data, there's no personally identifiable information, well, then it's kind of out of the scope of ethical issues. There's nothing to worry about. And so getting a more serious discussion about those consequences, I think is also important. And we welcome people to, if you have thoughts or examples that pop into your mind about that, to hear about those kinds of examples as well. It's not just science fiction at this stage. There are indeed examples now where we see algorithms playing a bigger role in what data we do and don't look at when we make decisions, as well as how those decisions are made or enforced.
Yeah, and I know we're running a little bit short on time here, but I can at least add a little bit more of my personal thoughts on this ethics slide here, which is that kind of the first thing is letting a RL agent explore in the actual world. That's not going to happen. That's totally unethical. We shouldn't have that probably ever happen. But in response to this, we have to basically do what Carl and I have been doing so far in our research, which is to rely on kind of simulated to rely on models of the real world. And in doing this, one of the things that comes up is that, let me just get back to the first schematic of RL here, which is that as a user, the user is deciding what the reward function is. And there's a lot of kind of consequences here, particularly in designing conservation agent, because, who is designing this reward function, and this reward function is really kind of determining the behavior that you will ultimately see from the agent. So kind of this whole kind of value alignment, where, how do you want your agent to like value certain things, or this whole problem is, it's a huge ethical concern in DeepRL, and something that I imagine there will be kind of maybe bespoke answers to in this conservation case. And this is something that we think is important and should be looked at. So.
Maybe we could take one more. I have a number of questions, but I'm going to save them for tea time. But maybe there's one more question. Andy?
I'm not going to make tea time, so I wanted to ask a question, because I think maybe other people have the same question. So one thing that I'm wondering is, with respect to, say, the fisheries data, when you're training agents, we're not really interested in the entire universe of possible fishing histories, right? We're interested in the conditional observations that we've had of our salmon fishery, say Chinook salmon fishery in the Columbia River, over the last X years. So when you're thinking about the eventual application of your trained RL agents to empirical data, are you thinking about these conditional cases, or how do you deal with that?
Yeah, very much. I think that's a great question. So one of the great challenges we have in fisheries management, right, is facing the environments we haven't yet seen. Like, how are those fisheries that we care about responding to a changing environment, right? And we don't have that data. And for most deep learning or statistical techniques, we have no mechanism to approach that whatsoever, right? Because looking at historical data just doesn't have the answer. So we have models now that can get closer to that approach, right? That can say, oh, based on some lab experiments, we expect population dynamics might respond in this way, but there's a lot of uncertainty, a lot of possible models, a lot of possible universes. And I think that's the kind of thing that we can explore with RL that you couldn't explore with standard methods. So you couldn't do an MSY or a standard Markov decision process. The problems are too big for that. But you could write down a simulation that includes, or many simulations that cover that, not the whole universe, but some of that space. And you can start exploring if agents can come up with effective ways or ineffective ways to deal with that. So it's really, think of it as just as a version of the kind of more limited stuff we do with scenario analysis right now. The RL can explore that world much more efficiently than just like classic scenario analysis, where we try only a couple sort of pre-canned policies.
You want to add anything, Marcus?
No.
Okay. So let's thank Carl and Marcus again, and we'll take a 5 or 10 minute break, and you can come back to this same Zoom call to join us for some discussion with your cup of tea or whatever if you want.
Sounds good. Thanks, Peter.
See you in a minute.
Thanks, Peter.